All right, looking at worksheet B for chapter 9. So starts off with number 1 here, making a sketch. We're going to put a couple things on that sketch. We're going to do a parabola. We're also going to do a line. And they only want this in the first quadrant. So a couple ways you could do this. One would just be to do some sort of an old school method where you just make yourself a little table of values. If we're going to stick in the first quadrant, that means I'm only using 0 through positive numbers. So you could just start by plugging in some numbers. So I plug in a 0, a 1, a 2, a 3, a 4, and then plot those on my grid. That would be fine. You could do the same thing for your line right here. Or for the line, just get y by itself, put it into slope-intercept form, and then just go from there. So if I got y by itself on this one, so if I subtract the x and then divide everything by -2, that would be 1/2 x plus 6. So you could just do traditional methods on that, where you put 6 on the y-axis and then go up 1 over 2 from there. So those are great traditional methods. Calculator way of doing this would be to simply just graph both. So on this one, you got your parabola, the 1/2 x squared. So I could put that one in. I could put in my line. I got the 1/2 x plus 6. And in this case, again, my window, let's just go from 0 to 10. And then on my y values, let's go from 0 to whatever. I don't know that it's going to matter, so let's just graph those guys. So there's the portion of the parabola, and there's our line. So to help me sketch the graph to some accuracy, just go into the table. So if I hit second, and then right here in the top right table, it said it only wanted the first quadrant values, so I would start with the 0 and then just work my way up to include some more points. But you can see this table is kind of nice because it gives you values for both graphs. So in blue it has the parabola. That's what I put in first. So there's some points that you could plot. And then for the line, there's some points that you could plot for the line. You only need 2 points to draw the line. So that would be pretty simple, but that's something you could take advantage of to make the sketch on that. So going on to part B, so find K, which is the x-coordinate of the intersection in the first quadrant of those two graphs. So again, 2 ways you could do this. If you wanted to do it by hand, you're looking for a point of intersection. So if you just set this equation equal to this equation, you could just solve that by hand. So if I do have my 1/2 x squared equaling my 1/2 x plus 6, I'm just looking for that point of intersection, so I could just solve that. Maybe start by multiplying everything by 2, so I don't have to deal with the fractions. And then from here, I'm just solving the quadratic, so minus x minus 12 equaling 0. So if I solve that by factoring, looks like x plus 3 and x minus 4 would give me those numbers. So solutions would be -3 and +4. Obviously we're in the first quadrant, so I would only keep the +4. So there's my x coordinate, and then if I just plug that back into either function, I can get the y coordinate. So let's just plug it right in there. So 1/2 of 4 is 2, plus 6 is 8. So there's the coordinates where they intersect, so easily doable by hand. If you did want to take advantage of a calculator, we just go under Calc and choose Intersect. And then if you put your cursor just anywhere near that point of intersection and hit Enter, 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 it gives you the coordinates of the point of intersection. So we could also get 4, 8 that way. So the area of the region bound by the coordinate axes, the line L and the line X equals K. So they're giving us some perimeters here to find an area under a region. We always know that means an integral whenever we're doing an area bound by a region like this. Alright, so it looks like in that last problem I went a little too far on that. I only needed that x was equal to 4 because we're not using that, but with the second part right here, so x equals 4. So keep in mind what we have for this. With the get a new sheet of paper here. So with the parabola that we have coming out right here, Then we got the line coming through right here. So a couple numbers that we already know. Obviously that's 0. These intersected where x equaled 4. And the y-intercept on the line was up at 6. And so we got that dotted line going through right here. So first thing they're asking for is the area of the region bound by the x-axis, the line for L, and the line equals K, which was 4. So first thing they're wanting to know right here is sort of this area right here. So to do that, we're just finding the area under this curve, and we're going to evaluate it from 0 to 4. So if we just take our parabola function on that and evaluate it from 0 to 4, then we can get the area under that curve. So for this guy here, just kind of standard integral process. So that's going to become x to the 3rd over 3. So a little cleanup on that. So you got your 1/2, you got your 1/3. So that's going to become the 1/6 x to the 3rd. So there's the integral for that function right there. And we're going to evaluate it from 0 to 4. So obviously the 0 is going to make it 0. So that's pretty simple. So if I just punch in the 4, 4 to the 3rd is 64 over 6, which we could reduce to just become 32 over 3. So that's this area right here. So where the x is sitting, we know that area is 32 over 3. So that's that area. So that was the answer to part D. In part E now they're going to ask us for the area between the two regions. And so what they did in part D was sort of lead us into that step, because all they really want is this area right here. But whenever you integrate a function, you are finding the area below it. So when I do the area below this line right here, I am finding all of this trapezoid that I see right there. So I'm getting that entire area. So if I only want the shaded part, I'm going to need to subtract out the area below the parabola that we had. So there we go. So if I took the area below the line from 0, so the line we saw up above was the 1/2 x plus 6. So we just want to integrate that. So pretty normal. You got your 1/2 x to the 2nd over 2. You got your 6x to the 1st over 1, which is just 6x. So let me do a little cleanup on that. I would call that first term 1/4 x squared. Then I got my 6x, and we're evaluating that from 0 to 4. Obviously the 0 is just going to make the entire thing 0. So really when I just punch in the 4, I'm going to get my answer. But I got my 1/4 4 squared plus 6 times 4, which is 24. So a little calculator work on that, or you could just simplify that in your head. So you got 16 divided by 4, which is 4, plus 24 is 28. So the 28 is the area of this trapezoid that we see right here. It is the entire area below this line. So if I now subtract out the 32 over 3, we're going to get just the shaded part, which is what they're asking for. So if I just punch in my 28 minus 32 thirds, and then turn that into a fraction, that would be the area of just the shaded part. All right, moving on. So jumping on down to number 3 now. So dealing with something kind of similar, we have the kind of an enclosed area that we're looking for. So this is always where the integral stuff comes in. So for number 3, we got this diagram, and it's already kind of showing us the highlights here. They're giving us right here the equation of the parabola. And this was kind of nice the way they set this up for us, because it's already in factored form, which means we already know the x-intercepts are at 2 and 10. So that makes that part kind of easy for getting those x-intercepts at 2 and 10. So that was nice. They labeled some points on us on the graph for us, and then we got the line AB kind of passing through it right there. So I'll write down the coordinates of D and E. The parabola's x-intercept. So again, that's the one we just kind of talked about. Obviously, if we set that equal to 0, we can get the x-intercepts. Since it's already been factored for us, we can just solve that for the positive 2 and 10 that we already got. So those would be our coordinates for D and E. So obviously, E is the first one, so E is going to be at 2, 0, and D is going to be at 10, 0. If this were not already in factored form, then remember you would just be solving a quadratic, and one way to do that is to then put it into factored form and solve it, or you could use the quadratic formula. But anyway, moving on, so find the coordinates of A, which is the parabola's y-intercept. Anytime you want a y-intercept, you plug in a 0 for x to get a y-intercept. So if I plugged in a 0 for my two x's right there, I'm looking at 1/5 times -2 times -10, which is 4, I believe. So for this guy, we're looking at 0, 4 for the coordinates of point A. So part C here at point B, the slope of the parabola is 4. So find the coordinates of point B. So, where they're giving us a slope, which, think of derivatives whenever we're working with slopes. So that's going to help us figure out part B, or point B, sorry. So for this one, so we have and they were talking about the parabola. So if I look at my parabola function, so you got that 1/5 x minus 2x minus 10. So for that, we know that the derivative of that equals 4 at point B. So that's going to help us solve for the x coordinate of point B. So to do the derivative, you'd probably want to put that into a bit of a friendlier format. So you're going to FOIL and then distribute the 1/5. So if you were to FOIL, you got your x squared minus 12x plus 20. And now if I distribute the 1/5, so I got my 1/5 x squared minus 12/5 x plus 2/5. And so I know that the derivative of that is going to equal 4. So I haven't done a derivative yet. All I've done is put it into a friendlier format. But here's kind of now the stage. Let me raise that up. Or if I do my derivative, so multiply the 2 to the front, subtract 1 from your exponent, multiply 1 to the front, and then subtract 1 from the exponent, so x goes away, your constant goes away. I know that's the derivative, and I'm setting it equal to 4. Multiply through everything with a 5, so you got your 2x minus 12 equals 20. So add the 12, divide by 2, and it looks like x equals 16. So we know the x coordinate is 16. If I take that 16 and plug it back into the original function up here, either here or here, I can get the y coordinate for point B, which if you do that comes out to be 84/5. Okay, so at part B, so one of the things we now know is the x value at this point was at 16. So we now know the line passing through there is occurring at 16. So find the equation of the line through A and B in that form. So a couple things we can now use. So the coordinates of B are at 16 and 84/5. So if I want line, line AB, a couple ways you could do it. Probably the easiest way would just be to understand that A was the y-intercept right there. So before we figured out that was up at 0, 4. So the easiest way is to, we can plug in the 4 for the B. All I need to know is the slope. So if I just do a little y minus y over x minus x, I can get the slope on that. So let's do that real quick. So if I did my y minus y over the x minus x, so we're just going to use that to get the slope, and then that's going to go in for M, 4 is going to go in for B, and you got the equation of that line. So you can work through the second part, you can work through the math on that. That's pretty simple to do. So let me move on to the area of quadrilateral OABC. So this guy is kind of like the one we had up above. There is a trapezoid taking place right here. So there's really two ways you can do that. you could just find the area of the trapezoid if you wanted to. So 1/2 the height times base 1 plus base 2 would not be a bad way to go. So the area of that trapezoid, if I did it that way. So the two bases have to be the two lines that are parallel to each other. So this is base 1 and this is base 2, which means my height is right here of 16. So there's the height. I got base 1 plus base 2. So that's one way you could get the area of that quadrilateral. Just do the area of the trapezoid. The other way is obviously with an integral. If you evaluate the area below this line from 0 to 16, it's going to give us the entire quadrilateral as well. So it should give us the same answer that we could have done with the trapezoid formula. Let's take a look at that really quick. So if we take the equation of the line that we just now found for part D, so y equals 4/5 x plus 4. And if we integrate that and evaluate it from 0 to 16, we should get the area below it. So do the integral process. So you got your 4/5 x squared over 2, which is going to give you 4/10 x squared, plus 4x to the first over 1. We're evaluating that from 0 to 16. Obviously, again, the 0 is going to give us a 0, so I just need to plug in the 16 to do that. So I did probably do that part in my calculator. I don't know what 16 squared is. So if I do my 16 squared times 4/10 plus 4 times 16, which would be 64. So that gives me the area of the quadrilateral, or the area below the line AB. Which would have been the same result that you would have gotten from doing the area of the trapezoid. So we got our 166.4 is the total area that we're given. So now we can use that information to now find the area of just the shaded part. So like what we talked about before, if I just want the shaded stuff, I'm going to take the entire quadrilateral or the entire trapezoid and get rid of these two pieces so that I can just have the shaded part left over. So I need to get the area below the parabola from 0 to 2. I also need the area below the parabola from 10 to 16. And once I find those, I can subtract those from the trapezoid in order to get the shaded part. So that's what we're now doing here for kind of the last stage of the problem. So the area below the trapezoid from 0 to 2 is going to be that x that you see right there. So we already expanded the parabola setup before, so let me kind of jump to that stage. So we're going from 0 to 2, and when we had expanded the parabola that they gave us, we came out with 1/5 x squared minus 12/5 x plus 4. So that integral is going to give us this area right here. So we'll start doing the integral process on that. So 1/5 x to the third over 3 is going to give me 1/15 x to the third. 12/5 x to the 2 over 2 is going to give me 12 over 10 x squared. And then you got your 4x to the first over 1. So there's our integral. We're evaluating that from 0 to 2. Again, that 0 is going to give me a bunch of zeros, so I really just need to plug in the 2 to get that. So 2 to the third would be 8. So let's call that 8/15. And then obviously 2 squared would be 4. So we got 24 over 10. Sorry, 4 times 12 would be 48 over 10. And then plus 4 times 2. So we got this area right here as 56 over 15. So that's something we got to get rid of from our trapezoid. And then now we also need to get rid of that x as well. So again, I'm taking the same function that we have right here, and I already have the kind of the setup for it. So let me just use what I already have. So I know the integral was 1/15 x to the third. And there's the rest of it. So I'm now evaluating that from 10 to 16. And I will have to plug in both of those. But again, I just now need to plug in those and subtract in order to get this area. So that's just plugging in numbers like we've been doing, so I'm going to let you do that part of it. But if you do plug in the 16 and get a number, plug in the 10 and get a number, and then subtract at the end, you'll get the area for that part of the x, or that x, as 216 over 5. So that's that guy. And so now here's where we can kind of finish everything off, sort of put it all together to get the shaded part. So we found the area of the quadrilateral to be the 166.4. So that was the entire trapezoid that we have right here. But I need to take away that area right there, which we figured out was 56 over 15. I also need to take away this area right here, which is the 216 over 5. So that can be left with just the shaded part. So obviously just do that part in your calculator, and that's going to leave you with just the shaded region.